So this instrument here is our GCMS. So this is a gas chromatograph with a mass spectrometer as a detector. This is a very powerful analytical tool employed in fields such as sports anti-doping, pharmaceutical industry and forensic science. This enables us to take a sample, vaporise it, separate out the different components of the mixture and analyse the masses of the different ions generated by components in that mixture. What I have here, if you can just see that very close up, in this small vial is a diluted sample of just ordinary unleaded petrol from a service station. Now petrol is quite a complex mixture, it has quite a lot of components in it that come out of the crude oil that it's been distilled from, and there are other additives as well that the fuel manufacturers put in there as well to improve engine performance. So we're going to inject some of that sample, which will be done automatically, into the instrument. The gas chromatograph will heat the sample to turn it into a vapour. The chromatography column will separate out the different components, and the vaporised sample in component form will travel into the mass spectrometer, where those species are bombarded with fast-moving electrons to turn them into ions, charged particles. And those charged particles register at the detector after they've been separated out by means of electric fields and subtle changes in electric current. The software is here, so we are going to vaporise our sample at a temperature of around about 250 degrees Celsius. The gas chromatograph itself, the chromatography column, runs at fairly low temperature because petrol has a lot of very volatile components in, so we don't need to heat the column very much to get a good separation. The sample is in place, so all I need to do is instruct the software to run our sample, and it will take a very small volume of that sample that I've shown you in the little glass vial, so 0.1 microlitres. This gives you an idea of how sensitive this technique is. I've diluted that petrol by a factor of 10 in another organic solvent, and that small 1 millilitre sample, it's only going to take a very tiny fraction of that. That will be sufficient to give us a good quality analysis. So I'm just going to now that I'm happy with everything, all the parameters seem to be correct. I'm just going to click run, and after a short delay we should see on the real-time screen here, the instrument data, we should see our mass spectrum and our chromatograph start to build up. So here we see the automated sampler in action. That will take a small volume of liquid from our sample vial, and the automated sampler also will wash the sampling syringe just to ensure it's free of contaminants. Take a small amount of methanol solvent, clean itself. So it's just cleaning with methanol now, and then it will inject our petrol sample ready for analysis. Injection has now been made, so the sample is actually in the instrument. It's in the heated injection chamber, so it will be vaporised and mixed with a helium carrier gas for transfer into the chromatography column. And after a short delay of 1 or 2 minutes, we will see a chromatogram and a mass spectrum start to be constructed on the screen in front of us. And both of those windows show what is happening in the instrument in real time. So after a period we call the solvent delay, which is designed to protect the inner workings of the mass spectrometer, the instrument will actually begin to acquire data, analyse ions, construct a mass spectrum and a chromatogram. So in the upper window we have the chromatogram. So this is the signal intensity versus the running time of the sample. So each of these peaks corresponds to a change in electrical current as ions arrive at the detection stage. In the lower window, this is the mass spectrum itself. So we have relative intensity on the y-axis, and instead of running time here, our x-axis is in units of m over z, mass to charge ratio. So this is telling us the different masses of species present in that sample. Okay, so that's just a sample of what we can do with this instrument, just to show that we've run something, we can acquire a chromatogram from it, and also the real-time mass spectrum. And the chromatogram in the top window here, we can take the data in that chromatogram, analyse it further using the instrument software, and from that derive mass spectra for particular peaks in this chromatogram, and then search those peaks versus a huge database that we've got and identify for a particular peak what the species within it corresponding to a certain mass are. For petrol, quite often in our experiments we're targeting things like what we call the B-Tex family of compounds, which are harmful to health, and that's things like benzene, toluene, ethyl benzene and xylene, which are problematic contaminants in fuels like petrol.